This video presentation is about our assignment 2, application of second order differential equations. Our lecturer is Dr. Sharifah Zurina Binti Nordin. We are from 1 SMJC section 3, group 4. Our group consists of 5 members, which are Darryl Yuhang, Nas Iqmal bin Mohamad Yani, Nur Amirah binti Ewanizam, Nur Izzi Farzana binti Roslan, Nur Sabrina binti Zainuddin. I will explain to you about the introduction. The linear differential equations are used to model many situations in physics and engineering. This works for systems including an item with mass attached to a vertical spring or string and an electric circuit with a series resistor, inductor, and capacitor. Second order linear differential equations have two types of solution, which are homogeneous equation and non-homogeneous equation. For our case, we use homogeneous equation when all the terms containing the unknown function are gathered on one side of the equation and the other side is identically zero. Based on our case problem, we employed the second order differential equation to solve the problems involving vibrating strings and damped strings. The motion of mass on a string when subjected to Hooke's law linear elastic restoring force is an example of simple harmonic motion. In this video presentation, we will discuss about the application of second order ordinary differential equation on vibrating string problem.
Okay, next, I will explain about the problem description for this assignment. In this case study, we were required to solve a problem related to engineering applications of differential equation. The problem involved vibrating spring with damping and without damping. By using second order differential equation, we were required to find an equation of motion for the system and the frequency of the oscillation of the vibrating string with damping and without damping. Hooke's law and Newton's second law are implemented to solve both of the problems. According to Hooke's law, the restoring force of the spring is proportional to the displacement and acts in the opposite direction from the displacement. So, the restoring force is given by is negative k in bracket s plus x. Newton's second law explains about the sum of the forces on the system, which is gravity plus the restoring force, is equal to mass times acceleration. So the equation becomes mx double prime equal to negative k in bracket s plus x close bracket plus mg. So the equation will be ks minus kx plus mg. In the equilibrium position, mg is equal to ks. So the differential equation will become mx double prime plus kx equal to 0. However, in real life, there is always some friction in the air system that will cause the oscillation to sort off slowly, and the effect is called damping. Because damping is primarily a force friction, an assumption can be made that friction force is proportional to the velocity of the mass and move in the opposite direction. So the damping force is given by negative bx prime for some constant b greater than 0. By applying Newton's second law, the differential equation will become mx double prime plus bx prime plus kx equal to 0.
Hello everyone. Now I shall be explaining on the first part of methodology, which is the overview of the methods used to solve the case study. Okay, let's move to slide 1. We must first analyze the case study description or statement before making our own judgment on the type of problem that we're dealing with, and in this case it is about damped vibrations of strings. Now let's take a look at its definition. The definition of damped vibrations mean that it is a gradual dissipation of a vibrating system's energy due to friction and other resistance until the vibrating system rests in its equilibrium position as a result of gradual reduction in frequency or intensity. From the case study description, we're also able to extract a key information, which is the second-order differential equation for damped vibration. And it is my double prime plus by prime plus ky equals to 0. We shall call this equation equation 1. And it is a homogeneous second-order linear differential equation. Next, to ease the process of solving, we need to change equation 1 to its auxiliary equation, which is am squared plus bm plus c equals to 0. And this is equation 2. After that, we need to solve the roots of equation 2 using the formula m1 equals to negative b plus square root b squared minus 4ac over 2a, and m2 equals to negative b minus square root b squared minus 4ac over 2a. After solving the roots for equation 2, and depending on the type of roots we get, we will be presented with 3 cases that influences the type of general solution that will be formed. For case 1, it is when b squared minus 4ac is greater than 0, and in this situation for our case study, it is called overdamping. This phenomenon occurs when the roots m1 and m2 are real and distinct, and the general solution that will be formed due to the condition stated previously is given by y equals to c1 e to the power of m1x plus c2 e to the power of m2x. Attached below here is the types of graph that represent the equation of the general solution above. Next, we have case 2. It is when b squared minus 4ac equals to 0, and this case is for critical damping. This phenomenon occurs when the roots m1 and m2 are real and equal. The general solution that will be formed due to the condition stated previously is given by y equals to bracket c1 plus c2 times x close bracket times e to the power of mx. Attached below are the types of graphs that represent the equation of the general solution above. Lastly, it is case 3. Case 3 is for when b squared minus 4ac is less than 0, and this case is for underdamping. This phenomenon occurs when the roots m1 and m2 are complex, which means that the roots have imaginary numbers. The general solution that will be formed due to these conditions is y equals to e to the power of ax times c1 cos beta x plus c2 sin beta x. Attached below is a graph that represents the equation of the general solution above.
Hi, so in this segment, we'll discuss about a problem involving a vibration system, which is one of the application of second-order differential equation, as well as the calculation used to solve it. So let's read the question. A vibrating spring with damping can be modeled by the differential equation my double prime plus by prime plus ky equals to 0. Problem A, if m equals to 10 kg, k equals to 250 kg per second square, b equals to 60 kg per second, with the condition of y equals to 0.3 m when x equals to 0 and y prime equals to 0.1 m per second when x equals to 0, we need to find the equation of motion for the system. Then we need to find the frequency of the oscillation, and lastly, we need to compare the result of this problem to question 8, which will later be shown in this video, and we need to determine what effect the damping has on the frequency of oscillation and on the solution. Before we start, let us understand the equation given. My double prime plus by prime plus ky equals to 0 is related to the vibrating spring. The m here is referred to the mass of object that is attached to the spring. B is
is referred to the damping force or damping constant. K is referred to the spring constant. Okay, the damping force here is it can be supplied by the air resistance or the force of friction at the point of the suspension. The damping will reduce the amplitude of the oscillation. Because of damping, its motion slows over time and eventually it will go back to its initial position. So we return to focusing on the problem A. Firstly, we need to extract the information from the question. We have here is M equals to 10, B equals to 60, C equals to 250, and with the following initial condition. Okay, the first step is we need to substitute all the values from the information into the differential equation, which will result in 10y double prime plus 60y prime plus 250y equals to 0. We need to ensure that the coefficient of second derivative must be 1. So we need to divide the equation by 10 and it will give this equation. To solve it, all you have to do is to write the auxiliary equation, and it is r² plus 6r plus 25 equals to 0. Once you have the auxiliary equation, we can solve it by using the quadratic formula, which is negative b plus or minus the square root of b square minus 4ac over 2a. So we'll just plug in the information into the formula and we will get the complex conjugate roots of negative 3 plus 4i and negative 3 minus 4i. So we need to refer back to the formula for the case of conjugate roots, and the general solution is y equals to exponential to the power of negative 3x times a cos 4x plus b sin 4x. Next, to find the specific solution, we need to first differentiate the equation by using the product rule. And we will get y prime equals to exponential to the power of negative 3x times negative 4a sin 4x plus 4b cos 4x minus 3 exponential to the power of negative 3x times a cos 4x plus b sin 4x. Then applying the initial condition where y equals to 0.3 when x equals to 0, we will get e equals to 0.3. And when y prime equals to negative 0.1, when x equals to 0, we will get b equals to 0.2. Hence, the equation of motion is y equals to exponential to the power of negative 3t times with 0.3 cos 4t plus 0.2 sin 4t. The next problem is we need to find the frequency of the oscillation. The frequency in a damped vibration is given by f equals to beta over 2 pi. So from the equation of motion, we can get the beta equals to 4 and substitute back into the formula and we will get the frequency is 0.64 Hz. For problem C, we need to first answer the question 8 and then compare the results. We can analyze that question 8 uses the same vibrating system as the original question. The only difference is that in question 8, there is no damping in the system. It can also be shown on the given differential equation where there is no damping constant. So we need to find the equation of motion and also the frequency of the system. To find the equation of motion, the step is similar to the calculation of original question. First, we need to substitute all the information into the differential equation and then change it to the auxiliary equation and then use quadratic formula to find the roots. Next, the general equation is y equals to a cos 5x plus b sin 5x. The next step is to differentiate the equation and we will get negative 5a sin 5x plus 5b cos 5x. Then, by applying the initial condition, we will get a equals to 0.3 and b equals to negative 0.02. Hence, the equation of motion is y equals to 0.3 cos 5t minus 0.02 sin 5t. The frequency of undamped vibration is given by f equals to beta over 2 pi. So from the equation of motion, we can get beta equals to 5. Substitute back into the formula, we will get frequency equals to 0.8 Hz. To compare, the equation of motion of the damped vibration is y equals to exponential to the power of negative 3t times 0.3 cos 4t plus 0.2 sin 4t. The frequency is 0.64 Hz, while the equation of motion of the undamped vibration is y equals to 0.3 cos 5t minus 0.02 sin 5t with a frequency of 0.8 Hz. The effect of the adding damping is it reduces the frequency of the oscillation. Evidently, the damped natural frequency is lower than the undamped natural frequency. The other effect damping has on the solution is the presence of exponential factor, which is a damping factor. It can be seen in the original damped vibration equation of motion, which is exponential to the power of negative 3t.
Hello guys, I'm Darryl from Group 4, and now I will present to you guys the results and discussion of our group. So the question that is examined in our math report is a damped harmonic motion or damped spring system. So as you can see here, the equations of tan y the prime plus 60 y prime plus 250 equal to 0 is actually the differential equation for this damped spring system. And this also considered as a homogeneous equation because it is equal to 0. So before we proceed, I would like to introduce to you guys about the three different types of damped spring system. First one is overdamped with the B square minus 4AC greater than 0. And the second is critically damped, B square minus 4AC equal to 0. And the third one is underdamped, B square minus 4AC less than 0. So in these particular equations, the B square minus 4AC is less than 0. It means that our damped spring system is an underdamped system. So this graph illustrates three different types of damped spring system, and the blue colors is our undamped spring system graph. For B and C is critically damped and overdamped. We are not further discuss about this B and C. We just want to focus on this underdamped system. For this A, the blue colors graph. So for the underdamped system, the restoring force is actually larger than the damping force. So it can still oscillating along the period while with the decaying amplitude and frequency. When the b square minus 4ac is less than 0, we have to apply the general equations of y equal to e to the power of alpha x over bracket a cos beta x plus b sine beta x. So this is the thing that we have learned in our lectures. Just plug in the values and differentiate it, and finally we get the answers of y equal to e to the power of negative 3t over bracket 0.3 cos 4t plus 0.2 sine 4t, and this is the equation motions of our spring system. So moving to the next sub equations, it requires us to find out the frequency of this damped spring system. So first, we have to note that there are actually two types of frequency. The first one is natural frequency, omega not equal to square root of t k over m, and this is only applicable to the undamped system. For the angular frequency, omega equal to square root of k over m minus b over 2m squared, and this for the undamped system. So in these equations, our system is a damped system. So we have to apply the formulas of angular frequency, omega. So just plug in all the values that are known. The k, m, and the p are all given in our equation. Just plug all in to find out the answer, and then find out the frequency. Also, frequency equal to omega over 2 pi. And this is the formula that we have learned during our high school days. So just recalling back the things, the knowledge, and then just plug in the values of omega and then 2 pi, and finally you get answers of 0.64 Hertz. And these are frequencies for our damped spring system. questions of our questions. So this question requires us to compare the result of our damped system with the undamped system. And what we can observe is that for the damped system, its amplitude and frequencies decreasing gradually along the period. Meanwhile, for the undamped system, its frequency and amplitude remains the same. And what we can conclude here is that the damping process will actually affect the amplitude and frequencies of the system by decreasing them gradually along the period. Also, when there's a case when it is a weak damping, when the omega naught is approximately equal to the omega. When this happened, only the amplitude will decreasing gradually along the period. Meanwhile, for the frequency will remain constant. But in this case, it's not a weak damping, so both the amplitude and frequency will decreasing gradually along the period. Okay, thank you. That's all from me.